Welcome back to the deep dive. Today we're going to try and visualize the invisible. We spend our entire modern lives just tapping on glass. You order a car, you buy a stock, swipe right, and most of the time it just works. But if you actually peeled back that screen, you wouldn't just find code. You'd find a massive invisible city.
That's a great way to put it, actually. It really is a city.
Well, think about it. You've got traffic control, massive storage warehouses, utilities, and the workers running around just keeping the lights on. And the scary part is, if just one piece of that city fails, one intersection goes down, the whole thing can grind to a halt.
It absolutely can. And that invisible city is what we call back-end engineering. It's the infrastructure that makes our digital lives possible.
So what I love about the notes we're looking at is they ignore the trends. They don't care about the hot new framework. They focus on first principles.
Which is really the only way to survive in this industry. I mean, the tools change every 6 months, but the core problems, they never change.
It seems like it. I feel like so many people try to learn backend by jumping into a boot camp,
Wow.
They learn Express or Rails.
Right.
And they learn how to type the code, but they completely miss the what and the why.
Exactly. They learn syntax, but they miss the architecture. The real goal isn't just to write an API that can, create, read, update, and delete data,
Yeah.
what we call CRUD.
That's the easy part, right?
Yeah, that's the easy part. A junior developer can do that.
Hmm.
The real mission is building systems that are reliable, that are scalable, and that are fault-tolerant. You're building something that can take a punch and just keep going.
Okay, so our mission today is to decode the three huge pillars from this roadmap. We're calling them the brain, which is all about databases,
Yep.
traffic control, which covers the absolute nightmare of concurrency and routing, and finally, the heavy lifting task queues and background jobs.
That's a solid plan. Those are the big three. If you
Yeah.
get those, you get the city.
All right, let's start with the brain, databases. And I want to start with a question that I think a lot of beginners are afraid to ask because it sounds too simple.
Okay.
Why do we even need a complex database management system? Like, why can't I just save my data into a text file on the server? It seems so much easier.
It does seem easier. And honestly, if you're the only user on a local machine, a text file works fine.
Right.
But the moment you scale to even 2 users, you run headfirst into what we call the concurrency problem.
The concurrency problem. Okay, break that down.
Let's use the example from the source material. It's perfect. Imagine you and I share a bank account. The balance is in a simple text file, balance.txt, and it says $40.
Okay, we have $40. I'm with you.
Now, at the exact same millisecond, we both try to make a transaction. You try to deposit $20, and I try to withdraw $20.
Okay, so mathematically, the balance should just stay at $40.
Right.
Plus 20 minus 20, net zero.
Ideally. But in a text file world, here's what actually happens. We both read the file at the same time. We both see $40.
Right, my computer doesn't know what your computer is doing.
Exactly. So your machine calculates 40 plus 20 is 60. My machine calculates 40 minus 20 is 20. Now, we both try to save.
Uh-oh.
If you save first, the file becomes 60. Then a millisecond later, I save my result, which was 20 right over your file.
Oh, wait, my deposit just vanishes. It's just gone.
Gone. Completely vaporized. And that's what we call a race condition. The last write wins, and your data is corrupted. A database is designed to handle that. It uses concepts like transactions and locking. It basically freezes that row for a microsecond, lets your deposit happen, updates the total, and then lets my withdrawal happen. It maintains integrity.
Integrity. I like that. It's like the database has a moral code.
In a way, it does. We call it ACID compliance in the industry. It guarantees the truth. And it does all this while managing the physical trade-off between disk and RAM.
Right, let's talk about the hardware, because we think of the cloud as this magic thing, but it's really just hard drives in a loud, cold warehouse.
Precisely. And the trade-off is simple. RAM, your main memory, is incredibly fast, but it's volatile. Power goes out, server restarts.
Everything's gone.
Gone forever. And it's super expensive per gigabyte.
Where's disk storage?
Disk storage, hard drives, SSDs. It's slower, but it's cheap and it's persistent. Server crashes, you reboot, the data is still there. Databases are basically masters of optimizing for disk.
Okay, this brings us to the great religious war of backend. Relational versus non-relational. SQL versus no SQL.
Oh yeah. People get very tribal about this.
They do. So what's the real difference?
Well, relational databases, like Postgres, organize data into tables with rows and columns. It's very strict. You have a schema.
The blueprint.
Right. If you have a column for price, the database will physically stop you from putting the word free in there. It has to be a number. It enforces integrity.
It protects you from your own sloppy code.
Yes. Non-relational databases like MongoDB are document-based. They're flexible. You can throw a JSON document in there, and if one doc has a price field and the next one doesn't, the database doesn't care.
So it's the difference between a filing cabinet and, like, a junk drawer.
That goes back. Yeah, it's pretty accurate. The junk drawer is fast to throw things into, which is great for unstructured data. But for your financial data, you want the filing cabinet.
And here's where it got really interesting for me. The source basically suggests that for 99% of people, you shouldn't even stress this choice. Just use Postgres.
Yes, this is a huge takeaway. Postgres has kind of become the gold standard because it's effectively ended the debate. It's a relational database, so you get all that safety and structure.
Yeah.
But it also has a data type called JSON-B.
JSON, binary JSON, right?
Correct. It lets you store flexible, unstructured data inside a structured table. And the magic is you can still query it efficiently. So you get structure where you need it for users and passwords, and flexibility where you need it, like for random profile settings.
So you can have your cake and eat it too.
Exactly. It simplifies your whole architecture.
Speaking of Postgres, there was this one detail in the notes that blew my mind, the varchar 255 myth. I feel like I see that everywhere in tutorials. Why 255?
It is everywhere, and it's a total relic of history. In older databases, like MySQL, limiting a text field to 255 characters actually had performance benefits. It was an optimization.
But in Postgres,
In Postgres, it just doesn't matter. Under the hood, varchar 255 and text-t are almost identical. The source argues you should just use text-xt, which is unlimited, and then enforce your length limit in your application code.
because if you set it to 255 in the database, and then your boss asks for longer usernames.
You're stuck doing a database migration, which is painful, it's risky, and it can lock up your whole database. Just use takext, change one line of code in your app, and you're done. It's about future-proofing.
That's a great tip. Okay, before we leave the brain, we have to talk about how it finds things so fast. Indexing.
Ah, yes. The book analogy from the source is perfect here. Imagine you have a massive textbook and you need to find every mention of the word concurrency. Without an index, what do?
I have to read page 1, then page 2, all the way to page 1000.
A sequential scan. It's extremely slow. But if you have an index at the back, you just look up concurrency and it tells you page 45, 112, 300. You jump straight there. That's what a database index does.
Okay, so if indexes make reading so fast, why don't we just index every single column, make everything super fast?
Trade-offs. It's always trade-offs. Every time you write something new or update a row, you also have to go to the back of the book and update the index.
Ah, so it speeds up reads, but...
It slows down your writes. Exactly. Over-index, and your database becomes sluggish every time you try to save. You have to find that balance.
Okay, let's move from storage to movement. Segment 2, traffic control, routing, and concurrency.
The nervous system of the city.
So a request comes in. How does the server know which piece of code to run?
That's routing. It's mapping an intent, like a GET request, and a URL to a handler, which is your code.
And the URL can have different parts. The source talked about path parameters versus query parameters. I always mix these up.
It's a subtle but important distinction. Path parameters are part of the resource's identity, like users 1, 2, and 3. That 123 points to one specific thing.
Okay, so that's the who.
Exactly. Query parameters are the stuff after the question mark, like sort desk, they're filters or modifiers. They don't change what you're looking at, just how you're looking at it.
Got it. Okay, so we've routed the requests. Now for the nightmare scenario. What happens when 1,000 people hit that route at the exact same second?
Well, if your server handles them one by one, synchronously, the first person is happy. But that 1,000th person, they're staring at a spinning wheel forever.
And nobody waits more than 3 seconds anymore, right? We have the attention span of a goldfish.
Oh, absolutely not. And so, to solve this, you really have to understand the two different kinds of work a server does. CPU-bound and I/O-bound.
Break those down.
CPU-bound is when the computer is thinking hard, crunching numbers, encrypting things, resizing an image. The brain is at 100%.
Okay.
I/O-bound input-output is when the computer's waiting for the database, waiting for the network, waiting for a file.
And the source said something crazy, like 95% of backend work is I/O bound.
It is.
Yeah.
Most web servers are just glue. And that leads to the waste. A modern CPU can execute roughly 3 billion instructions per second.
Okay, billion.
Now, your database query takes 100 milliseconds, a tenth of a second. If your CPU just sits there, blocked, waiting for that reply, you have wasted 300 million potential instructions.
300 million. It's like having a Ferrari and just letting it idle in the driveway all day.
Perfect analogy. You want that Ferrari driving other people around. So we've developed three main models to handle this.
All right, lay them on us.
First, you have threading. This is the traditional way. The operating system creates a separate worker, or thread, for every single request. 1,000 requests, 1,000 workers.
Sounds logical, more hands on deck.
It is, but threads are heavy. The OS has to manage them, they eat up memory, and switching between them is expensive for the CPU. You can't just spawn a million threads. You'll crash.
Okay, so what's option 2? The source mentioned Node.js.
Right. The event loop. This is what Node made famous. Imagine a single, super fast waiter in a busy restaurant.
Just one waiter, that sounds like a disaster.
It does, but he's non-blocking. He takes your order, runs to the kitchen, puts the ticket up, and immediately turns around to take the next table's order. He never waits for the food to cook.
Ah, he's always moving.
Precisely. When the food is ready, that's the database responding. The kitchen rings a bell, and he grabs it. It's incredibly efficient for I/O-bound work. That single thread never stops.
But what if a task is CPU bound? What if he has to, like, chop vegetables at the table?
Then nobody else gets served. The whole restaurant halts because the one waiter is busy chopping.
So great for waiting, bad for heavy thinking.
Exactly. Which brings us to Model 3, what the source calls the best of both worlds, Go routines, used by the Go language.
Virtual threads, right?
Yes.
Yes.
Instead of the heavy operating system managing threads, the Go runtime does it. They are incredibly lightweight. A normal OS thread might be a megabyte of memory. A Go routine is 2 kilobytes.
Wow, that's like 1,000 times smaller.
It is. It lets you spin up tens of thousands, even millions of them cheaply. You can write simple, step-by-step code like the threading model, but it runs with the efficiency of the event loop.
That's fascinating. It feels like we're constantly trying to trick the hardware into doing more than it should.
That's all it is, solving hardware limits with smarter software.
Okay, so we've got our brain, we've controlled the traffic, but sometimes the work is just too heavy to do while the user is waiting. Segment 3, the heavy lifting.
Yes, background jobs and task queues. This is all about user experience.
The source used the sign-up scenario. I fill out a form, hit submit, and I wait. And I wait, because the server is trying to send my confirmation email.
Right, and in that synchronous world, your entire sign-up fails just because the email server is down for a second. That's ridiculous.
It shouldn't be that fragile, so how do we fix it?
We decouple it. We separate the sign-up from the send email.
Walk us through it.
Okay, you hit sign up. My API saves your info to the database. That's fast. Then instead of sending the email, the API acts as a producer. It writes a little noted job that says send email to this user, and it drops that note into a task queue.
So like a literal inbox.
Exactly like an inbox, maybe RabbitMQ or Redis. And then instantly, the API tells you success, check your email. The spinner stops, you're happy, the app feels blazing fast.
But the email hasn't actually been sent yet.
Not yet. That's where the consumer or worker comes in, a total separate process. It just watches the queue, it sees the note, picks it up, and then sends the email.
So if the email server is down,
The worker tries, it fails, and this is the magic. It doesn't crash anything. It just puts the note back in the queue and says, I'll try again later. The user never even knew there was a problem.
And the source mentioned a specific retry strategy for this. Exponential backoff.
Yes. You don't want to just hammer a service that's already struggling. Exponential backoff means wait 1 minute, still fails. Wait 2 minutes, then 4, then 8.
It gives the system breathing room to recover.
Exactly. It's polite and it's effective.
That is smart. But what if it never works? What if the email is just wrong? Does it just try forever?
Chuckles. No, that would clog the queue. After a few tries, the worker takes that job and moves it to a special queue called the dead letter queue.
The dead letter queue, that sounds ominous.
It's basically a graveyard for failed jobs, but it's useful. Engineers can go look at it, see what went wrong, and fix the bug. It stops one failure from blocking the entire factory.
There was one more term here that we have to define because it sounds like a spelling bee word. Idempotency.
Idempotency. This is critical. If you don't get this right, you will absolutely lose people's money.
What does it mean?
It means that if you run the same task multiple times, the end result is the same as if you only ran it once.
Okay, give me a real-world example.
A task in the queue says, charge a user $10. The worker picks it up, charges the card, but then it crashes before it can tell the queue, I'm done.
Okay, so the queue thinks the job failed?
Right. It sees the job is still there. So it hands the job to a new worker. That new worker runs the charge again.
So I get charged $20.
If your system isn't idempotent, yes. And you will be very, very angry.
And I will unsubscribe.
Exactly.
Okay.
An idempotent system would first check, hey, Have I already processed transaction ID 555? If the answer is yes, it just does nothing and marks the job as complete. It ensures safety, even with crashes and retries.
That is absolutely vital. I mean, wow.
Yeah, reliability is the whole game.
So looking back at this roadmap, it really is a journey from, I guess, simplicity to resilience. You start with a database that guarantees truth. You add a traffic controller that ensures nobody waits. And then you add a team of background workers to handle the heavy stuff.
That's a perfect synthesis. A backend isn't just an API, it's a whole ecosystem.
So what's the big takeaway for our listener, if they're a junior dev or just curious?
The big takeaway is the concept of trade-offs. You noticed it in every single thing we talked about, right? RAM versus disk, SQL versus NoSQL, threading versus event loops.
There's no silver bullet.
Never.
Mhm.
There is no perfect stack. There is only the right stack for the problem you are solving right now. If you're building a personal blog, you don't need a massive microservices architecture with Kafka queues. That's just overkill.
You don't need a Ferrari to pick up groceries.
Exactly. But if you're building a stock trading platform, you absolutely cannot use a simple text file. You need the Ferrari.
It's all about context.
It's all about context. The best engineers aren't the ones who know every framework. They're the ones who understand the trade-offs. They know when to use the filing cabinet and when it's okay to use the junk drawer.
I love that. You don't have to know everything. You just have to know what you're trying to build.
That's it?
Well, that brings us to the end of this deep dive into the hidden city of back-end engineering. I want to leave you with a thought. The next time you open your favorite app and you pull down to refresh, just take a split second to imagine the chaos of traffic control, database locking, and background workers that just happened in that half second to show you your new messages.
It's honestly a miracle it works at all.
It really is. Thanks for listening, and we'll catch you on the next deep dive.
See you next time.